Hey, everybody. We're going to continue our conversation about sequences. So last time we were talking about, we defined sequences. I introduced you to a few of them, some ideas around them. Sequences are lists of numbers in a definite order. So this time we're going to start looking at the limit of a sequence. There's a couple of definitions that we'll talk about shortly. As well as this theorem at the end here. So that's what I want to go through in the next few minutes. There are plenty of examples that we'll have to do and things like that in other videos, but for now I just want to get these ideas out there. So we're going to start by looking at a sequence we've already seen before. So we've got the sequence 1 minus 1 over n from n equals 1 to infinity, and I wrote out the first few terms of the sequence here, right? So I want to look at this sequence a little bit differently. One of the things I said last time, let's remember this term here, we might write as a1, this term here is a2, this term here, oops, I wrote this wrong. This should be, I skipped one. This should be 2/3, then 3/4, then 4/5, pardon me. This would make this a3, a4, and so on. In other words, one of the ways I said that we can think about sequences is this is a function, right? If I input 1, out comes 0. If I input 2, out comes 1/2. If I input 3, out comes 2/3, and so forth. So we know when we have functions, our input-output correspond to coordinate points. We can think of our sequence the same way, right? So this first one would be the point 1, 0. The second one would be the point 2, 1/2. The third pair would be 3, 2/3, and on and on and on. So let's take a look at our sequence with this understanding. We've got a graph here. Oops, hold on, let me make sure I've shared the right page. Okay, this should be the graph. So I've got a graph here of these points as I just laid it out. Of course, Desmos is giving them as decimals, but those are the same fractions, on and on and on. Right? And one thing becomes pretty obvious when we look at this picture. Well, probably a lot of things do, but you might notice that these points appear to be getting closer to this line y equals 1, right? As we get a larger and larger n, we get closer and closer and closer to that line, right? We can see as we move out here at 67, we're very, very close to that line. Let's move out a little further. I went as far as 90. Of course, the sequence keeps going. I just didn't program that all in, but we can see how close we are to the number 1 in terms of the output of that sequence, okay? And this is the idea for the limit of a sequence. So let's go back to our definition. This first definition, right, the limit of a sequence. So the book has 2 definitions. We'll talk about the other one in a second, but let's just go through the definition. A sequence, the sequence a sub n has a limit L if we can make a sub n arbitrarily close to L by taking n sufficiently large. We write the limit as n goes to infinity of a sub n equals L, or we write a sub n goes to L as n goes to infinity, okay? So it's what we just noticed in that picture, right? In the picture we just had, we would say the limit is 1, because our points are getting arbitrarily close to L by taking n to be large enough, right? Or let's look at this a little bit differently. Let's go back to the algebraic form of this, right? So the definition of the limit says I can make this sequence 1 minus 1 over n as close as I want. So here, let me say it this way. A sub n is equal to 1 minus 1 over n. That's my definition of my sequence. And I'm making the claim right now that the limit as n goes to infinity of a sub n, or the limit as n goes to infinity of 1 minus 1 over n, is equal to 1. And according to the definition, what that means is I can make this sequence of numbers that I started writing up here as close as I want to the number 1 by making n large enough. So for instance, what if somebody challenged me to say, oh, can you make it closer than 1 over 100? Right? Well, all I have to do is take n larger than 100, and I get numbers like 1 minus 1 over 101, right? If n were to equal 101, larger than 100, then this is 100 over 101, right? That's 1/101st from 1, which is smaller than 1/100th, right? If you make the numerator bigger, it gets larger. And any number larger than 100 is going to have that same property, that the distance from one of the results is going to be less than 1 over 100. If you came back with a smaller distance, like 1 over 1,000, I simply do this, right? Now I'm 1/1001st away from 1, which is closer than 1/1000th, right? And you can give me any fraction and I can find a number n that if I get larger than that, all of the results are going to be closer to 1 than that, right? So that's what our limit is. Okay. Let's look at that second definition briefly. We're not gonna, just like in differential calculus and Calc 1 for us, we're not going to go into detail about the limits. The second definition is a more technical definition, but let's go through it briefly. Let's look again at where did he go? Let's do this. So here's our definition. Here's the second definition. A sequence A sub n has a limit L if for every epsilon, this is another one of our Greek letters, epsilon greater than 0, there is a number n such that L minus, the absolute value of L minus A sub n is less than epsilon whenever n is larger than capital N, right? And then we write the same limit definitions and so forth there. Okay. This is really just saying in a more technical term what I said before, what I said in those little examples. Let's look back at those. This here, this is like the epsilon. Somebody says, remember the definition said for any given epsilon, so this is the given epsilon. It's how close you're supposed to be, right? And then that expression they wrote in the definition, we want to make L minus A sub n less than epsilon, is just saying, well, this here is the distance the sequence is from the limit, right? The absolute value is another way of saying the distance, right? We don't care if our sequence is above or below the limit. If it's above the limit, this will be negative. It's below the limit, this will be positive, but it doesn't matter because we're taking the absolute value. And so all it's testing is how far away from this limit are we? And we can make our distance from the limit smaller than epsilon by making n large enough. And that's what I did here. I showed that if the distance I'm being challenged by is 1,000, I merely 1/1000th, I merely make n greater than 1,000, and my distance, so in this case, here's my A sub n, 1 minus 100, 1,000 over 1,001, absolute value is equal to 1 over 1,001, which is less than epsilon, which is 1,000, right? And will always be the case for n greater than 1,000. Okay. Don't get bogged down in that technical definition. We should have the same intuition about limits that we've had in our previous courses here. But I just wanted to expose you a little bit to this more technical definition. Let's look at the limit one more way. Let's look at a different sequence. Let's see. All right, so here's a slightly more complicated sequence. So this is the sequence where a sub n is equal to 1 plus 1 over n times sine of n. Okay. Now, I'm not going to go through too much working out the values here, but let's just look at this expression over on the left here and think about what's going to happen. We're always going to be starting at the number 1. Sine of n is always going to be somewhere between -1 and +1. Okay. Sometimes it'll be close to 0, sometimes it'll be closer to 1, sometimes it'll be closer to -1. And we're going to multiply it by something that's getting smaller and smaller and smaller as n gets larger, right? Sine will keep changing values. Sometimes as we get up to 1,000, it will be close to, maybe it'll be close to 1. As we get up to 2,349, it might be closer to -1. It'll kind of just keep going back and forth, at least appearing to be in a random way, right? So our distance from 1 is always, it's going to be sometimes above and below, depending on if sine is positive or negative. But the maximum distance away it can get will be bounded by this 1 over n, because if sine is always between -1 and 1, sine of n times 1 over n is always between -1 over n and +1 over n. And so now we look at the graph, these points are jumping back and forth above and below the line y equals 1. But how far they can possibly jump away is shrinking, right? So you notice as we move on, the oscillations, the up and down motion is getting smaller and smaller. And so even though these are crossing back and forth across 1, we would still say their limit is 1. Let's go back to that idea of challenging with a distance. So let's say somebody says to me, can you make this sequence be less than half a unit away from the value 1? So you notice these 2 vertical bars that I've put in here, right? Well, my sequence is always closer than those bars to the value 1. You can see this is the furthest point away, and they're continually getting closer. So somebody says, well, let's make this challenge a little harder. And so we pull these bars in. Let's pull them in quite a bit. All right. Pull them in this far. All right. So now someone has asked me to make my distance from 1 less than 1/10, right? Well, notice we start out much further away. We get closer, but we go further again, then closer, still closer than that, but then further again, then closer. And after about right here, we're always closer than that to 1. So again, we would satisfy that definition of the limit. The claim is that this limit is going to 1, and you can see that the values of this sequence at some point become closer than 1/10 away. So now somebody issues us a challenge to make it even closer. We simply have to go further out. And if they make it even closer, so here's a pretty small value, right? We would have to keep moving out along this graph. And at some point, those oscillations would be small enough that they're within those values, right? I've stopped my sequence at 90, but if we keep going on, these dots that represent the sequence are getting closer and closer and closer. Okay. So that's the idea of the limit of a sequence, which if you look closely is not very different. If you look at this definition and you go back to our definition of limits when we first studied them in differential calculus, it's not a very different definition. The only real difference is that n is an integer instead of any real number. Remember, we can think of these sequences as functions, and so the ideas we had about limits that we dealt with functions are still going to work with these sequences because they are functions. They just have domains that are only the integers. So let's let's go back one more time to that graph. And this time I want to look back at 1 minus 1 over n, that first sequence we looked at. So here's those dots again. Notice if I graph the function 1 minus 1 over x, all I've done is add in the domain, add to the domain. So now I have a function whose domain is going to be what I've graphed as x greater than 0. Right? So it's filled all those gaps in, but it's going through all the same points. And so this function is doing the same thing in terms of the limit as x goes to infinity that the sequence is doing, right? And this is how we're going to deal with, one of the main ways we're going to deal with limits of sequences. So let's go back one more time to our definition. This theorem here, if the limit as x goes to infinity of f of x equals L, and f sub n equals a sub n for all n greater than some integer n, then the limit as n goes to infinity of a sub n equals L. All this is saying is that if we have a function that looks just like our sequence when you plug in the integers to the function, then we can take the limit of that function and use it to find the limit of the sequence. Okay, so let's write this down and do one example to finish off. So this definition is telling me if the limit as n goes to as x goes to infinity of f of x equals L, and f sub n equals a sub n. Your book says for all n, I think. I wrote something like an f sub n equals a sub n for n larger than some integer n. All I'm saying is, as long as this is eventually true, sometimes our functions might not match up perfectly with the sequence in the beginning, but if after some, if after x equals 100 it always matches, we're talking about limits to infinity, so it's okay if strange things happen in the beginning. But as long as they match up eventually and stay matched up forever past that point, then the limit as n goes to infinity of a sub n is also equal to L. Okay, so I've just written that definition down again, and let's look at this with our sequence a sub n equals 1 minus 1 over n, and let's consider the function f of x. This was for n equals 1, 2, 3, and on and on and on. If I look at the function f of x equals 1 minus 1 over x, let's notice two things. The limit as n goes to infinity, as x goes to infinity of f of x is equal to the limit as x goes to infinity of 1 minus 1 over x. Using my limit laws, this is the limit as x goes to infinity of 1 minus the limit as x goes to infinity of 1 over x. The limit of a constant is just that constant, right? X changing doesn't change the number 1. 1 over x, as x goes to infinity, grows smaller and smaller and smaller. This limit is 0, so we get 1 minus 0 is 1. So the limit as x goes to infinity of f of x equals 1. So we've satisfied the first part of this theorem. The second part of the theorem, the second condition, notice, is that f of n is equal to 1 minus 1 over n, which is equal to a sub n, right? Here I'm letting n represent the integers. So I notice if I plug in an integer, I just get my sequence out. So I've satisfied the second part of the theorem, which means then the limit as n goes to infinity of a sub n is equal to 1, right? Because it's the same as the function, right? Which is what we had already discovered when we looked at our function, at least what we intuited from the image we saw on the graph of the sequence, okay? What this really boils down to when we want to talk about the limit of a sequence is we can almost always just treat them like a function, and we will use the limit laws and all the same rules that we developed when we were doing limits of functions to consider the limits of sequences. This only works when we have a nice form to put these sequences in, but most of the stuff we're going to look at is this way, and so we'll almost always be able to use these rules to find limits of the sequences we're interested in. All right, that's it for now.